Okay, hopefully you can see my cursor. If not, Bob, maybe unmute and let me know. So this is a talk I originally gave down in Phoenix in 2019 at the GSA convention there. The title then was Previously Unrecognized Cenozoic Structural Controls on River Courses Along the Eastern Flank of the Southern Rocky Mountain Epeirogen, with a focus on quote unquote Pikes Dome and interfluve high between the South Platte and Arkansas rivers. So for this talk today, we're going to take a look at some mapping I did of the Rocky Mountain Erosion Surface across Colorado. We'll talk a little bit about how other people have looked at the Rocky Mountain Erosion Surface. Then we'll start talking about deformation of the Rocky Mountain surface. And from there, we're going to focus on some large structural domes of the Rocky Mountain Piedmont area. And I'm going to focus you in on Pikes Dome. And then we'll start looking at how these Piedmont domes, specifically Pikes Dome, has rerouted rivers through time. And time becomes an issue. When did all this take place? So we're going to take a side trip over to the Florescent Valley, and I'm going to tell you that there's very good evidence there that Pikes Dome began growing in the Upper Eocene, which is different than a lot of other people think. A lot of people think it was started, may have started in the Miocene, so 20 million year difference. So I think all of you have, some of you have seen this. Bob and I and some other people have put a transect along I-70. We want to do a paleospastic reconstruction, want to pull in a bunch of data. And the thought was probably to get a whole, get a good handle on laramide structure. But if you're going to look at laramide structure, you better look at post-laramide structure and understand that as well. So as part of the transect, we go through the Eagle Basin, and there's a nice story that's been developed about dissolution of evaporites. So this map, the green areas are at about 10,000 feet, and that's a base level, an undisturbed level for Miocene basalts. So they're up at about 10,000 feet. You can see the horizontally striped areas. Those are Miocene basalts. And then along the upper reaches of the Colorado River, the Eagle River, down through Glenwood Springs, and the Roaring Fork River, some of those Miocene basalts have been dropped by as much as 4,000 feet, and due to dissolution of Pennsylvania and Permian evaporites along those rivers. And that, and some comments about South Park back in 2016, that this kind of wholesale evaporite dissolution had occurred in South Park, got me wanting to map the Rocky Mountain Erosion Surface. So what is the Rocky Mountain Erosion Surface? Well, you got your splitters and your lumpers. So you can think of the Rocky Mountain Erosion Surface as a low relief, mature surface that occurred after the basement uplifts of the laramide occurred. And so we stripped down to basement in a lot of places. And so we run into these flat surfaces in lots of places in the Rocky Mountains. And this is a little panel from a Van Tuyl and Lovering 1935 article. And it's just tabulating the number of surfaces that people have looked at. So Van Tuyl and Lovering were splitters. They had 8 to 10 surfaces, basically marked by things that occurred at common elevations. But Little, Lee, Worcester, Mather, they were looking at between 2 and 4 surfaces, depending on how Van Tuyl and Lovering wanted to rework some of their conclusions. And here's another panel from Van Tuyl and Lovering. So here they're showing three different surfaces, a lower flat top surface, and then as we drop to lower elevations, a younger Middle Eocene surface, Green Ridge, and then a little bit lower, the Upper Eocene Cheyenne Mountain surface. So they kind of looked around and they correlated things based on elevation. And here's another one of their diagrams. We're looking at Pikes Peak across what a lot of people call the Rampart Range surface. And a squint, I was squinting as hard as I could at this, but they've identified a variety of surfaces across what other people would just label as one surface, the Rampart surface. And I'm a little mystified by how they correlate these surfaces. They seem very close to each other. And here's a picture that Vince and Matt Morgan put into a CGS publication on the Rampart Range. But again, Pikes Peak and this pool table looking Rampart Range surface, quite impressive. And then some of you have been to my little cabin up in Goldfield. So we're on the west side of Pikes Peak over by Victor and Cripple Creek. And the guy who sold me the house owns all this land up on Big Bull Mountain. So I like to go hike up there. And very typically of a lot of these remnants of the Rocky Mountain Erosion Surface, you climb and climb and climb up a mountain. Suddenly you crest in this landscape, or a remnant of a landscape that's quite flat and gently undulating. And the top of Big Bull Mountain looks like a good candidate, and it's kind of dipping gently off to the south. And if you lie down on that surface and look up towards Pikes Peak, this kind of points up towards Pikes Peak. Now, Big Bull Mountain's made up of Pikes Peak batholith, Precambrian. But interestingly, up there, you can walk around and collect some exotic pebbles, rounded quartz pebbles, or these angular chunks of chert that I presume came out of the lower Paleozoic section. So it's an old surface that's had gravels and exotics washed across it, maybe some more proximal than others. Now, we're going to be talking about the Florescent Valley, and this part of the Rocky Mountain Erosion Surface is nicely defined by the Wall Mountain Tuff, which is an ignimbrite that came from the Mount Princeton area, Mount Etna area, and at 36.7, it was a day you didn't want to be in Florescent because its ignimbrite sheet swept across the mountains all the way out into the Denver Basin. So here's Denver, Colorado Springs, Canyon City, and Florescent, and blanketed that whole terrain. And so now we have remnant patches of it. And this is an Epis and Chapin diagram showing some of the late Eocene paleo drainages, a couple of which come out of South Park, the Paleo South Park drainage, and flowed down to Canyon City. And we'll be taking a look at those. And then they're starting to put some elevations on this surface. These numbers are elevations in feet divided by 100. So I got a little carried away, but I thought, I'm not quite visualizing this surface. And as a structural geologist, I like structure maps. And so I set out to really map the Rocky Mountain Erosion Surface. And I'm a lumper rather than a splitter. And I thought, if I'm going to make a map all the way across Colorado, I can't just look at areas that are covered by Wall Mountain Tuff in the Upper Eocene section. I'm going to look at overlap deposits that may be Oligocene in age, Miocene in age, Pliocene in age. And I'm really going to look at overlap deposits all the way up to the beginnings of Pleistocene glaciation. The idea being that I'm trying to get as close as I can, perhaps, to an Eocene erosion surface, but the best I can do is work with what's there now. That surface isn't everywhere preserved, but I'm going to create a map that I think will get me as close to that as possible. So here's my rationale. In places I have overlap deposits, and those are happy areas, and I would then take the base of those overlap deposits and I would get an elevation for that. And those become my best data points for this Rocky Mountain Erosion Surface, which is shown here in red. In some areas, I've got subsurface points, so I can go to wells, like down in the San Juan Sag, or I can go to seismic in the San Luis Basin, or I can go to gravity in the San Luis Basin, and I can shape out how deep some of the tertiary valleys are and give you datums on the Rocky Mountain Erosion Surface from the subsurface. And then in areas where I have no overlap deposits, I add in what I call supersurface points, and they are simply points at or above the current topography. And typically, I'll go to points of highest topography to define that. But what it gives me is a map that is continuous all the way over the high peaks and down into the subsurface. And that is how I can get continuous coverage across all of Colorado, and as we'll see, some of the neighboring states. So I compile a bunch of detailed geologic maps. Well, let's take a look at this. So here's a compilation of 2-degree sheets for Colorado. And sometimes if all I have is a 2-degree sheet, I'll use that. But here's my methodology. I'll compile and georectify detailed quad maps, and those are 7.5-minute quads if I've got them. And I import those maps as KMZ files into Google Earth, and then I pick elevation points for the base for the Rocky Mountain Erosion Surface in Google Earth. And I do that by just hovering my cursor over a contact, say a base of onlap, and Google Earth shows me an elevation for that point. And then I save that point using the elevation as its name. Then I can group those points into folders by different overlap deposits. So I've kept track of, if I'm using Miocene basalts, I'll have a folder for that. If I'm using the base of the Wall Mountain Tuff, I'll have a separate folder for that. And then, of course, I have folders for my supersurface points and for my subsurface points. I'll export those folders as KML files to Excel, and then I can rearrange stuff, pull out the datums, and contour the data using Surfer. And it becomes a pretty big task. Here's a CGS index of some of the 7.5-minute quad mapping that's been done. Well, there are 1,938 quads in Colorado. Not all of them have been mapped, but to georectify and collect and bring these into Google Earth, it takes a while. So here's my map of the Rocky Mountain Erosion Surface for Colorado. And a couple things jump out, or should jump out at you. The cold colors are lows, and the warmer colors up to white are the highs. So we see, for instance, the San Luis Basin, the upper Arkansas Valley, Browns Park area up in here, some of the high peaks around Leadville. Here's Pikes Peak, for instance, the Front Range. So things that the San Juans, these should be familiar to you. So my next question is, well, what does all this mean? How can I characterize some of these areas? So, you know, just a quick sweep for these larger features, I can break out, say, in green structural basins. So again, the San Luis Valley, upper Arkansas Valley, Browns Park area, We get over into South Park, we have the Chase Grabens by the Elkhorn Thrust, things like that. So I can populate the map with that. We can go back to those dissolution areas over in the Eagle Basin in purple. And there's another nice one at the Antero Reservoir area, the Antero Syncline at South Park. We've got laccoliths, like down in the La Platas, the western part of the San Juans, the Gothic area, Crested Butte. We've got laccoliths. We've got some big flank uplifts adjacent to the Rio Grande Rift, the Swatch Range, the Southern Gore Range, parts of the Sangre de Cristos in here. So we can, and then there are things like basement uplifts down in the San Juans. We also have some of those. And then these blue areas are the very large, subtle Piedmont domes. And in particular, I'm going to be talking about this one, which is Pikes Dome. And it goes all the way from kind of the Guffey area all the way out into western Kansas. So they're very large features, and we're going to talk about how they've rerouted the rivers. You can already see kind of a radial drainage pattern off some of these subtle domes. So in 2018, our geologic study group had a field trip in Ouray, and I confidently stood up there and pointed to my Rocky Mountain Erosion Surface map, and you can see the data points that go into it. And I said, well, look at this low here. And the Uncompahgre River in Ouray, where we were standing, nicely flows down the low. And I said, here's an example of 25 of original relief in the Rocky Mountain Erosion Surface with a river cutting a 2,500-foot canyon right down through Ouray. Man, got this nailed. But these things look very spectacular on a map, but we have to always remember that when you put them to one in a cross section, they get to be quite subtle. And you really need to ask yourself, is this really original topography, or could this be later deformation of the Rocky Mountain Erosion Surface? So we put a cross section through that low over a couple highs. This one's over by Lake City, between Lake City and Ouray, and then this one's over by Mount Wilson, southwest of Telluride. And this is a vertical exaggeration of 12:1. And again, here's the 1:1 section up top. But the Rocky Mountain Erosion Surface is the dashed red line. And here it's covered by San Juan volcanics. So you see in the light pink are deposits of San Juan volcanics on top of it. Over in this area, the orange color is the Telluride conglomerate. And below it, in this area, we've got Precambrian basement. And then as we get over toward Mount Wilson, we've got mixed Paleozoics and Mesozoics, and then laccoliths. And what's really telling, the real way to figure out if this is a structure or original topography, the best way to nail that it's got to be a structure is to look at current directions. And fortunately, the Telluride conglomerate goes from very coarse-grained cobbles on the east to much finer as you go to the west. And there are scattered examples of current directions. So here we have a beautiful example of an inverted drainage. The Telluride conglomerate's been picked up over Mount Wilson and created this inverted drainage. Streams don't flow uphill. So we've nailed the fact that that is a structure or deformation of the Rocky Mountain Erosion Surface, not original topography. And then you can see here, this is a basement high that Bob Reynolds likes to call a tumescence. A volcanic tumescence may have uplifted the basement over in here. And he figured that out by walking between Ouray and Lake City last summer. And here we are high up staring at Uncompahgre Peak in the distance off here. We did 9 days in the San Juans walking through this terrain. It was great till we got chased out by snow. So let's now switch over and look at those Piedmont dome areas. And this is the Southern Rocky Mountain Epeirogen as defined by Eaton. And he's really just looking at smooth topography in meters. So here's Colorado. And as you know, the high peaks of Colorado indicate the crest of this Southern Rocky Mountain origin. And what interested me were these crenulations on the east flank. And if you've ever worked with gravity data or regional magnetics or something like that, you often like to think in terms of regional trends versus local trends. And when I look at this, I see noses is closes. So if we can subtract out the regional trend, which would be this broader Rocky Mountain Epeirogen, which has tilted everything off to the east, we can get a better sense of the amplitude, the magnitude of some of these noses or closes out in the Piedmont area. So let's first look at regional topography. So again, here's Colorado and Wyoming, New Mexico. And already in the regional topography, you can see a high nose up at the Wyoming border. This would be the Gangplank area. Come down into central Colorado, and you've got this nice topographic nose in the Pikes Peak area. Pikes Peak is right there. So this would be Monument Hill. And then you can go up onto Raton Mesa, so climbing up to the New Mexico-Colorado border, and there's another large one there. So that's regional topography. And then if we take a look at my Rocky Mountain Erosion Surface, we can see those same features expressed in the Rocky Mountain Erosion Surface. So what I would say is the current topography is an expression of underlying structure. And the other thing you notice as you look at this is that the rivers are flowing down the lows between these highs in the Rocky Mountain Erosion Surface. So again, they would be in places representing radial drainage off a structural high. And just the data that's gone into this, for eastern Colorado alone, I had to grab about 4,000 of my Rocky Mountain Erosion Surface structural datums out of 10,000 that I had for the whole state, and then add in stuff for eastern New Mexico, eastern Wyoming. And from the USGS, I use contours in the base of the High Plains Aquifer, which represent tens of thousands of water wells. And I fortunately didn't have to repick all of that, but I am going to have to repick that surface up in this area of northern Colorado, southeastern Wyoming, and parts of Nebraska, because their datums are not always on the base of the Cenozoic. They're at the base of the aquifer, which is not always the same. But it's pretty good, and it's a good start. The other thing we're going to look at now is how other people have looked at the surface out in this area. So this black line running north-south at 104.5 is a common profile for the other studies that have come out in the literature. And then I found this white box is where I can directly compare the mapping they've done. So we'll take a look at that. So here's the minus 105 north-south transect. And first off, the red lines are my Rocky Mountain Erosion Surface line. So we're going south to north. Dash line is my definition of the Rocky Mountain Erosion Surface. The brown line is current topography. And then the black line here is how Eric Leonard at CC mapped the base of the Ogallala. You can see some differences between, I would use the base of the Ogallala out in eastern Colorado as my Rocky Mountain Erosion Surface, but as I come west, I'm dealing with some older overlap deposits like the Rocky Mountain erosions, like the Wall Mountain Tuff. But as I look at this, I see a big discrepancy between what we've done, he and I. And he has taken this southern flank of the Raton Mesa High, and he's connected over to the northern flank of the Pikes Dome High. This would be Pikes Dome, this would be Raton Mesa. And so he gets maximum erosion and maximum isostatic rebound focused on the Arkansas River, where I have a distinct low at the Arkansas River rather than a high. So we're about 180 degrees off from each other. Well, Eric's interpretation, I think, is kind of continued through the literature. Here's Beth McMillan in 2006. And again, she doesn't have it quite as high, but she's just connecting the Raton Mesa High with the top of the Pikes Dome and doesn't recognize this structural low at the Arkansas River. And she's defining a surface she calls the Rocky Mountain Basin fill. So basically the erosion surface plus whatever sediment would have been deposited on top of that is the surface she's trying to get at. We can look at Carl Karlstrom, and he's defining a Miocene paleo surface. And again, when we look at the Arkansas River, no indication of structural low at the Arkansas River. He connects pretty much the topographic highs to each other to smooth things out. So he's assuming that at 10 MA, these topographic lows were full of Miocene sediments. And I would say, I don't think so. I think that there's been structural deformation of these surfaces here. So I think here you end up overestimating the amount of fill and removal, and therefore overestimating the isostatic rebound. And then Lazier et al. Kind of even compound the issue where they anticipate they had a 10 MA surface that was very high over the Arkansas River with lots of denudation and erosion, and they build in an even greater high across the South Platte River. And then you can compare these surfaces. So here's current topography up here. Here's my Rocky Mountain Erosion Surface. Here's Eric Leonard's Ogallala surface. Here's Beth McMillan's base of fill surface, and then Karlstrom's paleo 10 MA paleo surface, and Lazier's paleo 10 MA surface. So you can subtract the surface minus the topography, and you come up with residual maps. And here's my residual map, and it's got not a lot of relief because my map looks a lot like the current topography map. But when you look at Leonard, McMillan, Karlstrom, and Lazier, you see this odd anomaly along the Arkansas River. And over here, you start to get these anomalies at the South Platte River and up at the North Platte River. I think these are artifacts of their technique. And again, I think they're giving them too high estimates of late erosion and therefore too high estimates of isostatic rebound. And you can also do a correlation coefficient between these two surfaces, and no surprise, I get a higher correlation coefficient when I compare topography to my RMES than when you compare topography to their other surfaces. So what I said when we looked at the Southern Rocky Mountain Epeirogen is that I want to subtract out a regional trend surface. So to define the regional trend surface, I take points along the major rivers on the RMES. So I'm only sampling my RMES along these major rivers, which are flowing down lows adjacent to these structures. So this is a kind of a smooth trend line across the eastern Piedmont. And then I can subtract that regional trend surface from the Rocky Mountain Erosion Surface, and the remnant now gives me the amplitude or the height of the residual. Really makes the domes pop out. So here we have a relatively subdued one at the gangplank, and I'm suspicious of this because of the mapping of the High Plains Aquifer. I'm going to redo this area up in here. But Pikes Dome is robust and pops out. It looks like it's got about 800 meters at its apex, and that's not including Pikes Peak proper, which looks to be a little structural pop-up. We can all talk about that. And then Raton Mesa has up to 900 meters of relief on it. And then we get some scattered things out here. There's a little bit of noise once you get down into the weeds, but look at Pikes Peak. It goes all the way out well into western Kansas, and we're going to see this again. So now we're going to look at some river profiles. So I'm going to do longitudinal profiles down some of these river courses through time, and we're going to again see some of the drainage inversion like we saw down in the Uray area with the telluride conglomerate. And I just want to mention, this is a beautiful painting by Bierstadt, and we're looking across the Rampart surface at Pikes Peak. So always appreciate a beautifully done picture. And, you know, I met Tom Stephen, who was one of the founding members of the Florescent Scientific Society. Met him a couple times. Feel sad that I never had a chance. This really wasn't on my radar screen at the time to talk to him about Pikes Dome, but he was onto this story, and I think some of you may have been on field trips where he mentioned it, and I'd love to hear your recollections of what he had to say. But we have a couple publications from him that address this. One is with Evanoff and Uhas from 1997 from RMAG, and what he's showing here are a couple ages of drainages. So we're going to visit the Castle Rock drainage with the Castle Rock conglomerate, which goes from Clear Creek down to Calhan. We're going to visit the old Terriel South Platte system, which goes through Florescent, and these are thought to be upper Eocene drainages, the ones in yellow. And then, as Cal mentioned, we've got this divide Arickaree drainage, which appears to be younger, and we'll talk about the possible ages for that. So keep these three drainages in mind. There are lots of other reported Miocene drainages. I think Cal thinks a lot of these may be, in fact, younger than Miocene. And then we have a second publication that came out in the Bill Braddock symposium that the CSS put together in 2004. And Tom had a couple things, and Dan Shaw was part of that effort. Then we think Jennifer Shaw, who may be Dan's daughter, was involved in that. He talked about timing, and a lot of these meanders were initiated along low gradient streams and then rejuvenated to uplift to the Front Range beginning in the middle Miocene, caused those drainages to incise. So what he's talking about are some of the incised meander loops we see like along Clear Creek and a lot of the canyons going up into the Front Range. But keep this middle Miocene, so 13 million years age in time. And then at the southern end of the Front Range, he's talking now about what I'd call Pikes Dome, and it's a very interesting comment. He says at the south end of the Front Range, a structural platform more than 20 miles across and surmounted by the prominent Pikes Peak protrusion, also developed during formation of the incised terrain. So again, he's seeing this platform or dome, but he thinks it's occurring in Middle Miocene time. And then we get this statement: ancestral South Platte River flowed south from the vicinity of Florescent to the Arkansas River near Canyon City It was a meandering stream that occupied a low gradient valley. It became antecedently entrenched along the flank of a rising topographic and structural ramp that offset upper Oligocene volcanic units at the west margin of the Pikes Peak platform. And we're going to revisit that, but timing here is important. Again, he's thinking that Pikes Dome was active from middle Miocene onward. So looking at those three drainages I pointed out before, we'll start first with rock paleo drainage. This is an article by Koch, 2018. And basically the Castle Rock drainage flowed from Coal Creek Canyon, where we have where it picked up clasts of the Coal Creek quartzite and carried them 75 miles to the southeast to Calhan here. And these are the outcrops along its trend. And Steve Keller and Matt Morgan did a very nice comprehensive look at current directions in the Castle Rock conglomerate. Here's a picture of theirs from Castlewood Canyon, beautiful trough cross-bedding, planar cross-bedding showing southeast flow. And this is down at Castlewood Canyon, and I'm sure a lot of you have been to that. And here's just some clasts of the Coal Creek Canyon the Coal Creek quartzite I picked up at Coal Creek, so at the source, and we get this stretched pebble metamorphosed conglomerate. In some places, the pebbles are very well defined. In other areas, you get just kind of a blue-gray quartzite, and you don't see a lot of the pebbles. And they show up in the Castle Rock conglomerate. So they're carried from Coal Creek to the southeast. The other thing that shows up nicely is the Wall Mountain Tuff. So we get clasts of the Wall Mountain Tuff, and it appears at the Castle Rock conglomerate. Probably Bob Reynolds thinks you're breaching volcanic dams, and there are massive floods that are carrying the fragments of the Wall Mountain Tuff shortly after it was erupted down the Castle Rock drainage. And out of Calhan, this is what the Castle Rock conglomerate looks like as far as we can chase it. So right there is a clast of Coal Creek quartzite, the gray quartzite, and then you get a lot of these clasts of Wall Mountain Tuff and basement material and things like that. So that's out at Calhan. So we'll look at a profile along the Castle Rock drainage, so northwest to southeast across Pikes Dome here. And for these profiles, again, topography is in brown. The pink or red line is my Rocky Mountain Erosion Surface. The blue line is my regional trend surface. So at the rivers, say South Platte, the Rocky Mountain Erosion Surface and the trend line meet each other. And again, down at the Arkansas, they meet each other. Now, in terms of data out in here, we don't have a lot of constraint on the Rocky Mountain Erosion Surface. We've eroded beneath it. But downstream, we have a very good datum of around 10,000 meters as the Ogallala comes on. And upstream, we have outcrops near Canyon City that are at 17.5, so we can bracket where the Rocky Mountain Erosion Surface would be. It's about in the middle there. As we come across the axis of Pikes Dome, so this would be at Monument Hill, we have the Rocky Mountain Erosion Surface up at about 2175 meters. And we can see as we come to the South Platte River, we've inverted this Castle Rock Paleo Valley. So we have about 700 feet of relief between the South Platte, where the stream is now running uphill to Monument Valley, and then we've just assumed that it eventually flowed somewhere down to the Arkansas River over in here. So we've got a dome axis of about 500 meters, and we've got inverted drainage, so a beautiful example that this has to be a structure. This isn't just original topography on the Rocky Mountain Erosion Surface. Then we can look at the South Platte Terriol system. So now we're coming down through the Florescent Valley, and this is a map from Epeirogen. And these are late Eocene Paleo valleys. So the thinking is the current South Platte, which is shown here in cyan, originally flowed down and into the Florescent Valley, and then down through the 4 Mile Creek area, Graben, down into Canyon City, at least to the Arkansas River and possibly beyond. So we'll take a look now at its profile. So here we have a north-south profile along that old drainage. And again, topography in brown, Rocky Mountain Erosion Surface in pink, and from the South Platte River up by Florescent over the divide just south of Florescent, we get this inverted drainage. There's about 650 feet of relief where that stream is now flowing up. The old South Platte River is now flowing up. So we have this inverted drainage. And we'll look at the Florescent lake beds, which are developed just north of this dome axis where we get the inverted drainage. And we'll take a look at that in detail. Oh, the other thing we have down here is this very important datum right down at Canyon City at the Arkansas River. And we also have datums, hard datums of overlap deposits somewhat higher than that as we come up the Rocky Mountain Erosion Surface. And there are many other points that define this, but these are kind of critical points that are important for the regional shape of the Rocky Mountain Erosion Surface. And down at Canyon City, here's one of those outcrops. And it's a little outcrop of Gribbles Park tuff and Oligocene lahar held up by a little basaltic intrusion. But there are a couple of them, and they occur up on these hills above. You can see the houses below, but there are these little conical hills where it's preserved. And here's a picture of the lahar, and then big class of this Gribbles Park tuff, which is Oligocene in age. So critical data points. And then we'll look at what's shown as a Miocene river on that original Stephen et al. Map that we first looked at. So we're looking at the Divide Arickaree River, which heads off to the east. So here's Florescent here. Here's Lyman here. We're going to take a look at some stuff in Lyman. And then it heads off in this direction. Now, in terms of the big question mark here is what's the age of the Divide River? And as I said earlier, Cal Ruhlman thinks parts of it may be as young as Pleistocene. Parts of it he thinks may be older. Pearl originally thought that this Arickaree River, he found clasts of fresh Pikes Peak batholith in cores out in northwest Kansas, and that's how he originally got onto this. But he thought this river was late Pliocene into very early Pleistocene. Stephen et al., Scott, and Epis et al. Thought this was a Miocene river, and I'm an agnostic. I think it could be as old as Oligocene. And right now we've collected a couple samples, and the CGS is dating samples of the Divide gravels. So that would be from right down in this area as we speak. Bob and I went out and took a look at the Sherwood Forest neighborhood, which is just west of Divide. And the landowner there up on the top of the hill has nicely collected a bunch of local cobbles that are parts of the Divide gravels. So we didn't want to steal his landscaping, but he assured us they were all gathered locally from around his house. You can also go to the Divide gravel outcrop at Twin Rocks Road and Route 24, also west of Divide. And here's what the outcrop of the Divide gravels look like. So a lot of these are volcanic cobbles. They came out of the 39-mile volcanic field. There's some reports of even Cripple Creek breccia in these gravels. I haven't definitively found one. I've been a little suspicious when I've seen stuff that looks like Cripple Creek breccia, so younger, about 30 million years. Some of it looks like it might have been brought into some gravel pits. So I'm a little bit confused with that. And then Paul Denny, who's a member of FSS, nicely called me up, sent me an email, and said, you know, out in Lyman at the golf course, in the flower bed next to the tee for the driving range, there are cobbles of Coal Creek quartzite. And I thought, wow, I've never heard that. So there was a long saga. The whole town got involved in seeking out where this landscape material may have come from. And Bob and I went out. In fact, yeah, it looks like Coal Creek quartzite at the golf course. And we went to a gravel pit just east of town, north of I-70. And lo and behold, there are abundant cobbles of Coal Creek quartzite, white to gray Coal Creek quartzite, and then cobbles of various forms of volcanics, and even a nice cobble of fountain formation. So there's stuff. And Glenn Scott went out to Cedar Point, which is just north of Lyman, saw these volcanic cobbles and said, this is 39-mile volcanic material. So we've got Pikes Peak granite out there. We've got 39-mile volcanic material that really should be analyzed in more detail. We've got Coal Creek quartzite. We've got fountain formation carried by this Dividerickery River out to the east. So here's the longitudinal profile for it. And we go from the Florescent area over in here. We come uphill to about Divide here. So we have a nice example again of an inverted drainage. We drop down to Woodland Park. We cross the Ute Pass Fault, which has offset the Rocky Mountain Erosion Surface. We do get Divide gravels up on the Rampart range here, and then we head off to the east, so through the Castle Rock conglomerate. So another example of an inverted drainage and an obvious offset by this structure. Further evidence that this is deformation of the Rocky Mountain Erosion Surface, not original relief. And in this case, Pikes Dome is showing about 800 meters of relief at its axis, and that's not including the top of Pikes Peak. So now let's talk about how these structures have caused the rivers to become realigned. So if we start with just the outlines of the various domes, Gangplank, Pikes Peak, Raton Mesa, in the upper Eocene, we have a series of southeast flowing rivers, some coming out of Wyoming into northeastern Colorado. Here's the Castle Rock conglomerate. We have it preserved from Coal Creek down to Calhan. And then I've projected it down into southwest Kansas. And I'll mention that quite recently, John Smith and his co-workers have been looking at cores of the High Plains Aquifer, so the Ogallala, and they're finding it dates to the Paleogene, not to the Neogene. So they're finding older, the Ogallala out there is dating as older than originally suspected. So it'd be White River equivalent, not what we think of as Miocene Ogallala. And in their cores, they've got some Precambrian gray quartzites, and I've been after him to tell me, do you think that's Coal Creek quartzite? And apparently the ages they're getting from the zircons out of it would be compatible with it being Coal Creek quartzite. But I've never heard him say, oh yeah, they're Coal Creek quartzite. And then over here we see the Terriel South Platte system going down at least to the Arkansas River, and it may have extended off to the south. And then the Arkansas River, based on the work by Zhu and Fan, they believe that the upper Arkansas originally flowed south through the Wet Mountain Valley down through the Raton, the Huerfano and Raton basins. So we have these series of southeast flowing rivers, and they're about to be disrupted by growth on these domes. So by the Eocene-Oligocene transition, a couple things happen. One, the Terriel South Platte system gets blocked by the rising Pikes Dome to create Lake Antero and Lake Florescent. And the Arkansas River that used to flow down through the Raton now gets shunted off into its present course between the growing Raton Mesa High and the Pikes Dome growing. Now, for those of you who are really familiar with this area out here, that your immediate reaction should be, well, wait a minute. The dome didn't block the South Platte River or Lake Antero. It's the volcanics that blocked it. So let's investigate that. So we're going to do a little diversion. I'm going to come back to this river evolution story after we visit the Florescent Valley. So in the Florescent Valley, we get lake deposits formed. These are deposited at 34 million years ago. So we're talking about the Upper Eocene. You all know about the beautifully preserved fossils within the lake beds, and then interlayering of volcanic tuff and things like that. And we can go back to 1883, probably the second USGS report that seems to discuss Florescent in detail. And these guys pretty much saw evidence for Pikes Peak Dome. And they're talking here about the South Platte River. So they say the ancient outlet of the whole system was probably at the southern extreme. So the thing was flowing to the south. At least the marks of the lake deposits reach within a few meters of the ridge. The ridge is the dome axis, which now separates the waters of the Platte and the Arkansas. So they're talking about the drainage divide south of Florescent between the South Platte River to the north and the Arkansas River to the south. And originally, South Platte River drained across that drainage divide. And the nature of the basin itself, the much more rapid descent of the present surface on the southern side of the divide with the absence of any lacustrine deposits upon its slope. So they're going to the drainage divide south of Florescent, and they're trying to make the case that there are no lake deposits south of the current topographic drainage divide, which isn't really right. And we're going to address that in a minute. At the last elevation, so they're saying that at the last uplift of the Rocky Mountain chain, the drainage flow of this immediate region was reversed. So they're talking about inverting the drainage, the elevation coming from a southerly or southeasterly direction, perhaps Pikes Peak. So they're seeing an axis of this dome off to the south or southeast, maybe Pikes Dome. The lake or series of lakes was drained dry by emptying at the northwestern extremity. The drainage of the valley now flowed into a brook which followed the deeper part of the former floor, and the waters of the region have since emptied into the Platte and not the Arkansas, passing in their course between Topaz Butte and Costello's Mountains. So in 1883, these guys are very much talking about the model that I'm talking about. And here's a Google Earth view. We can look to the north up to Lake George, where this valley would be at an elevation of 8,050 feet. We can come through Florescent and south of Florescent to the current drainage divide at 8,650. And then once we cross that, we drop down to 8,150. Here's Pikes Peak. The red line is the axis of Pikes Dome, and it looks like it meanders all over the place, but we're looking all the way 60 miles out to Calhan, which is right here. So in the current topography, you can see how this drainage has been bowed up and over the axis of the divide. And they saw that as well back in the 1880s. But the other story out there is, no. These valleys were blocked by the 39-mile volcanics, which came out with Epis in the mid-1970s. And so that, you know, in this case, okay, the volcanics block these lakes in the Upper Eocene, but it doesn't mean that the dome axis was present at that time. It may have come in later, like in the Miocene, when people think a lot of this deformation started occurring. So let's get into the details of Florescent. Florescent is blessed because there are lots of outcrops of wall mountain tuff. We have very good handle on the shape of the Rocky Mountain Erosion Surface. So here are 100-foot contours on that surface, and you see there's a low here along the blue, which is the which is Lake Florescent. I think I have a slide out of order, but we'll find out. Just a second. Okay. This is the Florescent Valley. This is where the Tarryall Creek came down and flowed down to the South Platte, and the South Platte out of South Park joined it to flow down to Canyon City. So we see a low where the South Park fork of this is, a low where the Tarryall fork of it is, and those lows have been bent over the dome axis here. So we actually come up along the valley axis and then drop down along the valley axis. And that's due to the dome folding it. The green in here is the Lahar Dam. And unfortunately, somehow I'm missing some. Okay, well, we'll not worry about that. Here's a picture of the Lahar Dam. This is down at Evergreen Station on County Road 1. So volcanics that came spewing from the Guffey area. Here's Lake Florescent and dammed the valley at Lake Florescent. So here's the Lahar Dam. And if we look at the Wobus and Epis map, all these little pink dots, and unfortunately they look a lot like some of the basement colors, but these are all wall mountain tuff outcrops, and then we have the lake deposits. So we have very good control for the shape of the Rocky Mountain Erosion Surface, and we have these kind of gentle 100-foot contours. So we have good mapping, we have good control of the Rocky Mountain Erosion Surface, and what I decided to do was just look at a series of profiles across, transverse profiles across the valley, and I've selected a few of them. So we're going from Lake George down to the Lahar Dam with these transverse profiles, and just did them quickly in Google Earth. So we get topography, we get the red, which is the presence of lake deposits. And then the black lines are just, I'm sketching in what might be the base of them just by connecting the outcrop points. And then the other thing is I'm looking at this and I say, well, these are all lake deposits. Maybe there was a lake level up at this level. So I'm just connecting the outcrops across the highest point of the lake deposits. Typically it came in pretty flat. This is tilted slightly, but here's down at the Lahar Dam. Here we're crossing an oxbow. So we go, we're coming downstream through this. It takes a turn and then swoops around this mountain in the oxbow and then continues on down to the south. So here's the main channel. And if I look at the difference between what I have exposed at the surface and this inferred lake level, down at Lahar, I have 160 feet of Lahar. Then I come into the lake deposits at the drainage divide. I've got about 65 feet of lake beds. As we go up toward Florescent, I've got about 200. And as I go to Lake George, I've got 75. So then we can line these up using the inferred lake level as a flat datum, going from Lake George down to Lahar Dam. And I thought this was pretty interesting. It could indicate that the dome is growing while the lake was there. So you need the Lahar Dam to partially back up this lake, to dam the lake, yes, but the base of the valley floor is actually being uplifted across the drainage divide. So there's some indication that the dome was active at this time. I wasn't really very satisfied with that, because it could just be that at the dome axis, you've lifted it up more than these other areas. Maybe you've just eroded more of the lake deposits away, and that's why you're getting this thin here. And then if we look at current structure, so we're not flattening on the inferred lake level anymore, we see we've got, about 650 feet of relief between Lake George, the dome axis, and then we drop down toward the Lahar Dam. So as again, well, I was intrigued by that, but not particularly excited about it. But I said, okay, let me finish the exercise. The key is always to look at all of your data. And what's quite interesting in the Florescent Valley is that there are lots of water wells that have been drilled for the ranchettes out there. So there's about 1,000 water wells available. And of those, 300 have lithology logs. And if I go in there, I can break out basic lithologies. They talk about granite for the Pikes Peak batholith, which would be the base of the valley floor. They talk about shales and sediments. Those would be the lake deposits. And then they talk about volcanics, and those would be where you are in the Lahar fill for the valley. So the blue lines on here are now structure contours, 100-foot structure contours on the base of the valley. And I only carry those contours as far as I have control. So in a lot of places, these water wells reach total depth without reaching the bottom of the valley. Well, I haven't projected the bottom of the valley, but what I want you to appreciate is we have one set of contours on the Rocky Mountain Erosion Surface. These are 100-foot contours. They're widely spaced, and you get the sense of a gentle, relatively gentle surface. And then you get these blue contours, which again are 100-foot contours, very closely spaced. There is a buried canyon under the Florescent Valley. And how big, how deep is it? Here we are down by the Lahar Dam, and I can go between a well that has Pikes Peak batholith at the surface, so you're out of the valley completely. And I can step 400 feet to the east and find a well that has at least 520 feet of volcanics, so you're still in the valley. And what that represents is a greater than 55-degree canyon wall right there. And in profile, what does it look like? We have the gentle valley up above that we all can look at the surface, but hidden in the subsurface, as shown by the water wells, is this very steep canyon wall. So there's a cryptic canyon under the Florescent Valley. And so what's the meaning of that? What is that? Well, and then again, we can now add that back to our longitudinal profile. And here's what the minimum depth of the incised canyon floor would look like going from Lake George over to the Lahar Dam. And then this is its current structure. So again, we have some indication possibly of Pikes Dome, and then it continues folding later in time. So let's talk about timing. So we've got the Wall Mountain Tuff that blankets this gentle Rocky Mountain Erosion Surface valley at 36.7. And then we start to see the initial Pikes Dome uplift represented by the canyon incision between 36.7 and 34.1. Then the Lahar Dam comes across, blocks that canyon, and we get the Florescent lake fill. So that's at 34.1. And then subsequent to that, we get continued uplift of the Pikes Dome and inversion of the Platte River from 34.1 to 0 MA. And in a little more artistic view, we have this low gradient Rocky Mountain Erosion Surface. We start the uplift of the Pikes Dome and we get this very deep incision that creates the canyon. So the river at this point is an antecedent river. Then the Lahar Dam comes, blocks that canyon. We back up the lake deposits at 34.1, and subsequent to that, we continue this folding. So I think this is just a beautiful example of timing where we can nail when this Pikes Dome initially came up. And it started coming up back at the end of the Eocene, not during mid-Miocene time. So let's go back to our progression of evolution of these uplifts. And so we were at the end of the Oligocene with the damming of the lakes. And now between Oligocene and Miocene, the way I've done this is I preserve the old river courses, put them in cyan when they're no longer active. And what's active at this time slot would be dark blue. So the Arkansas has already changed its course. We saw that in the last time frame. The Pikes Dome axis is now still blocking the South Platte River. It can't ever get over that dome axis, won't ever get over that dome axis again. And it looks like the South Platte now gets shunted off to the east to become this divide, a Rickery River that Pearl originally noted and Tom Stephen noted. Now, what's interesting in Pearl's report, these purple lines are the drainage patterns on the base of the Ogallala. So because of the thousands of wells out here, they've got enough detail that they can see the incision pattern beneath the Ogallala. So it's a pre-Ogallala incision pattern. And Pearl noted this prominent drainage divide out in western Kansas. Well, these are his lines. And I've, subsequent to that, after picking the dome axis, added the dome axis. Well, the dome axis is at the drainage divide. So here is evidence out in western Kansas that the dome was active prior to the deposition of the Ogallala. And as I said before, we're not even quite sure what the age of the oldest Ogallala is. It's thought often to be Miocene, but we're finding new data down in this area that it's Paleogene from the core data. So here's another indication of Pikes Dome being older than people might have suspected. So we have this divide, a Rickery River, and then as the Pikes Dome continues to grow, we seem to get an additional uplift, and I think it's involved with the Cripple Creek intrusion at 30 MA that blocks the divide, a Rickery River. And the South Platte is now shunted off to become its current South Platte along the margins of the northern margin of Pikes Dome. And it explains why you come down and you get this pretty much left-hand turn at 11 Mile Reservoir of the South Platte. And instead of continuing south like it originally did, it heads off to the northeast into the Platte River as we know it today. So the conclusions for that is these second-order structural domes punctuate the eastern margin of the Southern Rocky Mountain Epeirogen, and they are structures. The major trunk drainages follow structural lows in the RMES. The doming has altered the course of rivers over time, and the doming has been active since the Paleogene. Now, I want to put all of this in a little wider context and explain a couple things like why we see this change in the general trend of these rivers. And I go back to work I did in the 1990s on the magmatic sweep across western U.S. So what we're talking about here is the beginnings of the severe and laramide orogenies, or the severe and laramide orogenies. What's fueling those? Coney et al., Dickinson, Bird, many people have talked about the flat slab subduction of the Farallon plate beneath the western U.S., and I think it's a great model. And so at the time, I took all of the magmatic ages and put them into a space-time diagram. So here we go from 120 million years down to 10 on the vertical axis, and distance from the trench. So this is the space-time diagram. I did a series of these profiles, strike sections, dip sections, and basically map the time-space volume as a three-dimensional volume. And from that, we defined a leading edge of the magmatic sweep. Here it is, red and blue, and then the trailing edge of the magmatic sweep in pink and green. And what we see is, through time, the magmatism swept from west to east, stalled out, and then rolled back and went from east back to west. So this is called the advanced sweep, the rollback or return sweep. The front of the duckbill would be here at the transition. And we mapped this in time across the western U.S. So there are state profiles here. So the red line is shown with the red contours, and they go from old to young as the magmatic sweep sweeps out to the east. Here's Colorado. And then the blue shows where we roll back to the southwest. So here's the corridor, and we go from older during the rollback to younger contours sweeping back to the southwest. And then we looked at structural styles. So we looked at thrust belt contraction. We looked at early basement uplifts. We looked at late basement uplifts. We looked at extensional basins like the San Luis Basin. And then we looked at metamorphic core complexes and compared them on the map to this bracket of what the plate was doing at the time. And found this one-to-one correspondence. So we get early contraction, we get this transition period where we get some contraction and some extension, and then we break into full extension and metamorphic core complex development through time. So we see this times transgressive, space transgressive shift in structural styles, but they're all acting in concert with the subducting slab behavior. More recently, Copeland et al. Published this paper, and looks like here we go. We've got their reference here. But he did his own sweep diagram, so age again on the vertical axis, distance from the trench. But he added in the eastern sweep of the foreland basins. So the youngest marine sediments are these lavender diamonds. And then the blue circles are the thrusting, so severe and laramide thrusting basement uplifts. And then these orange boxes are the extensional basins. And what's interesting here, these stars are indications of high topography. And that's really what I want to get at here. Because with oxygen isotopes, Paige Chamberlain looked at oxygen isotopes, which are a way of getting at paleo elevations. And what he found is that through time, so here we are at 59, where we're just beginning to see that magmatism sweep from east back to the west. So we call that the slab rollback period. He's got high elevations, and as you come through time, they step down to the south and southwest. Unfortunately for Colorado, he doesn't have much data. So what I've added in here are, this is a drainage divide that Emmett Evanoff has spoken about recently, and Sealand et al. For the Middle Eocene had a continental divide and huge drainage divide centered up in Wyoming. And then later in time, and so the rivers at that time on the east side of that drainage divide are pointed to the southeast. And that's at the end of the Eocene. So we saw at the end of the Eocene that rivers were flowing to the southeast. And then I believe that I put the Southern Rocky Mountain Epeirogen on here. By 28 and after that, it's moved down into Colorado, and now the rivers are basically radiating off it to the east. So that we may be seeing this southern migration of the Rocky Mountain Epeirogen through time. So just as a summary to put us in a broader context, I always trying to think in broader context. What are the significance of these shifting rivers and these uplifts, and how do they fit into a broader context? And I think it's part of this magmatic sweep. I'll call it the severe laramide or orogenic cycle. And we start with flat slab subduction. The magmatism in the Foreland Basin shift to the east by 1,400 kilometers or so. We get all these contractual structures, be them thrusts or basement uplifts. We then get this slab turnaround, and you can think of this point as that Farallon plate is basically stalled out. It's not changing its geometry, and it's still subducting at a high rate, 500 kilometers per 10 million years or something like that. But it's starting a relatively structurally quiescent period. So the magmatic front is stable. This is when I think we get the penaplanation and the development of the Rocky Mountain Erosion Surface. Subsequent to that, that slab starts steepening and magmatism shifts south and west. We get the big ignimbrite flare-up. The volcanics blanket this eroded surface, the Rocky Mountain Erosion Surface. We start to see these major extensional structures like the San Luis Basin. And they, of course, as Bob Reynolds has pointed out, they open up the big accommodation space during this time. That's where you get real thick accumulation of Cenozoic deposits. It's in these extensional basins. And then in the wake of the slab, the asthenosphere starts to upwell. As it departs to the west and south, the asthenosphere is coming up to fill that void, and it's creating these epirogenic uplifts. And as that slab rolls south and west, we see a southward migrating epirogenic uplift. And as those domes appear and disappear across the landscape, they're rerouting the rivers continuously, and we get this series of roving rivers. So the South Platte goes from flowing south to suddenly flowing northeast. So being a structural geologist, I see that the structure types track slab behavior through time and space. And now as I've become more familiar with the Cenozoic record, we can think about river behavior tracking slab behavior. And I'd also throw out, basically, are we still in the laramide? Well, the laramide's part of a larger orogenic cycle. We're certainly still in a phase of this orogenic cycle. Anyway, so that's the end. What I like to tell people is, you see some things every day and they kind of go by you. You may not even notice them, but try to think about them differently. Try to get a different perspective on things you think you're quite familiar with. And no telling what you'll come up with. So thank you very much. We did it under an hour and a half, not too bad. Okay, thank you all. And I'll open it up for questions. Or Bob, do you want to do that?
I note that Lewis posted a question in the chat.
Okay. Can you read it to me? I'm not seeing it.
Has the Pikes Dome, which extends to Kansas, played a part in the development of spatially associated petroleum systems?
Well, let me just say this. I haven't found a giant oil field under Pikes Dome yet. The other thing I would note is that these are extremely subtle features. If you think about the dip that's imparted in these, it's way less than 1 degree. So you have a lot of existing structure in the Mesozoic rocks that underlie Pikes Dome that really control what the dip of the units are. So if you're thinking about just up dip oil migration, Pikes Dome hasn't radically modified the underlying dips that were imparted, when the Denver Basin developed earlier. So I haven't seen a big direct connection between oil migration and this dome development. I do see a big connection between what the rivers are doing and what our highways are doing when we get snow over Monument Pass. But so no, I haven't discovered an oil field this way.
Scott Miner asks, what is controlling the east-west trends of the domes?
I don't know, Scott. I think it's probably some secondary flow of the asthenosphere. I can never say that very well. But I have not seen, I don't have an explanation for why they're trending the way they are. It could be, I may need to look at when you form a north-south dome like the Southern Rocky Mountain Epeirogen, do you set up east-west structures of a certain orientation, or do you set up east-west structures? But no, I don't have a good answer for that.
I see no more questions in the chat.
Okay. Well, what's going forward is, can we get some decent dates on this Divide Arickaree River? I'd like to see some chemical analyses of the volcanics out by Lyman and Cedar Point that Glenn Scott thought were 39-mile volcanics, and hopefully the work that the CGS is doing right now to try and date the Divide gravels at Divide bear fruit, and we get a better handle on that. For me, the next part is to remap the base of the Cenozoic up through northeastern Colorado, southeastern Wyoming, and parts of South Dakota. And that'll put some changes into the Rocky Mountain Erosion Surface map up in that area. All right. Are we good? Going once, twice?
Lewis asks, where else is slab rollback recognized? Good question. I don't know if it's been recognized in the Andes. Bob, do you have any insights there? The reason for flat slab subduction, some people evoke higher convergence rates of the Farallon plate. Other people talk about the subduction of what they call the conjugate Chatsky plateau, or so there's an oceanic plateau with lesser density that gets subducted beneath the western US, and they think that that's why the slab didn't dive as quickly. I'm kind of an agnostic on that. I haven't found any of my own data to say one way or the other what the cause is, but it is a pretty unique phenomenon that we even get this flat slab subduction. So a lot of the Andes stuff I've looked at, we're dealing with fairly typical flat, plate subduction along the margin of South America. But yeah, there are examples of flat slab subduction, and they see segmentation in the subducting slab, and that can set up areas where you have different degrees of different attitudes of slab subduction, and there are examples of that down the Andean margin. But whether there's slab rollback, not on the order that we're seeing here.
Yeah, Ned, I think one of the big differences is the Andes is so narrow. I mean, we see these processes of flat slab subduction down there, even in today's seismic records, but it's a very narrow system. So to answer the question, I think that really the Western United States is it might be the only place that we know of in the world where there's such a broad region. I mean, the point that the laramide deformation took place so far away from the plate margin is something that's, almost unique.
Yeah.
And so that's part of it. Hey, Ned, I wanted to just quickly ask you a question about Cripple Creek and the timing of that. You had one diagram where you showed a sort of a dark blob on the Cripple Creek structure. And I'm just wondering if there might have been some volcanic uplift or, thermal doming or something associated with the Cripple Creek timing.
I'm going to say yes, I do think so, Bob, and I'm going to do some more work on that. Can you see my slides?
Yes, we can.
Okay, so here's what you're talking about.
Yes.
Something had to disrupt this divide Arickaree River, assuming that it went all the way to the 39-mile volcanics, which is why some chemical analyses of these boulders would be helpful, some age dates of those boulders. But it appears that there's quite a prominent late uplift that has deformed this divide Arickaree River. And not only that, but if I look, let's see if I can get to this. If we look at the profile for the South Platte River, if we look at the profile for the South Platte River, here's the dome axis I focused on, but look at this down in here. You've got the Rocky Mountain Erosion Surface way up here. You've got the current topography way down here. There's all kinds of headward erosion that's taken place along 4 Mile Creek. And I'm suspicious that this headward erosion may be related to that later uplift that you noticed, Bob. It all depends on how you lump some of these uplift indicators. And I don't have a lot of data to go by. I'm trying to get back to this map. Yeah. So we'd be talking about this uplift continuing down into this area.
Yeah, it would just be a
drainage.
It'd be interesting if there. I mean, I'm noticing a parallel between this and your example from the Telluride conglomerates on the other side of the state, and those were associated arguably with laccolithic type and subcutaneous intrusions or something. And
tumescence, as you call it.
Well, I was dancing around that word, but yeah. So here you're showing me tumescence in your outhouse at Victor, and
yeah,
it might be important.
Well, speaking of my outhouse, I'll just say that it took me 30 years to realize I was driving uphill from the South Platte River to Cripple Creek for about 50 miles, and that's when the lights started to come on that, damn, there's a big uplift here. So,
hey, Ned, could you go back to that slide that you had just a second ago to answer the question?
The river profile for 4 Mile? There you go.
Yeah, I'm glad you brought that one up because I had the question when you first showed it. Could you just tell us exactly what that datum of 2230 is based on? What
It would be based on a hard overlap point. So I'd have to go back to the map, but I suspect it's a Rocky Mountain. I mean, I suspect it's a Wall Mountain tuff or 39-mile volcanic outcrop that I've grabbed the base of.
Okay.
And then there are many others up in here, Vince. But what I wanted to post on here was this low datum at, just south of Canyon City. And then where do I have the next data? What I consider really hard data would be up in here.
I guess what I'm not understanding, if it's above the topography, are you projecting it in from somewhere?
Yeah, because, this topography is running right down 4 Mile Creek. So you're in the canyon.
Okay.
So adjacent to you, you have a datum that the map is based on that comes across this canyon. So there's nearby outcrop at this level that defines the Rocky Mountain Erosion Surface. So
Okay.
yes, it's projected just in, from the edge of the canyon, but the actual topography as I go straight down this current drainage is down here. Yeah.
Thank you.
Does that make sense?
It does.
Okay, good. All right. Any other ideas? What do we do next? Well, it'd be a good field trip, but any other thoughts on scientifically how to attack this further? Oh, Vince, I had a question for you. What is the South Platte lineament? Why does the South Platte follow that lineament, between the northern part of the Rampart Range and Devil's Head?
I don't know, but it goes a lot farther than just in the mountain front. If you watch, it goes way out on the plains. The South Platte follows it with that same orientation way out on the plains. So I don't know what it is, but it's certainly something fundamental.
Because I think Bob's asked me, okay, you got these, uplifts occurring, but how do the rivers actually shift their courses? Do they just walk their way across the landscape, or is it stream capture, or what is it? And that's the part that I haven't worked out. But it seems like there's something aiding in sending the South Platte River off to the northeast, and it's some kind of a structural element.
The question there is that rivers are very good at incising, and we've got in Colorado we've got killer examples of rivers that have just carved their way down through the basement like it's butter. And the Black Canyon of the Gunnison is one.
Royal Gorge.
The inside, Royal Gorge, the inside meanders of St. Vrain and Cache-la-Poudre. So I'm just curious about the rivers. What makes a river move? And I think Ned hit it on the head. I think it is piracy. I think piracy is what makes rivers move. I think otherwise rivers stay in place. And we've got infinite examples in the Colorado Plateau of rivers that are still in place from 10 million plus years ago. Those river courses were set over 10 million years ago, and they're still there today as the incised meanders of hundreds of examples in the plateau. So to get a river to change its course is a big deal, and it has to do, I think, with piracy. And I think there's the whole chapter, the Pirates of Colorado. I mean, they'd make an opera about it. There'd be a musical. It could be awesome.
All right. I'll let you work on the musical, Bob.
Excuse me, I had put in two things in the chat, and maybe they're too ridiculous to even address because I am not a real geologist.
And who is this? Who is this?
Catherine.
Okay. I don't see the chat, so somebody could read it.
Oh, okay. Hang on, I'll pull it back up. I had just closed it so I could see your demonstration here. Hang on. Oh, there it is. Okay, the first one was in the graph that you had made that you mentioned had the duckbill.
Yes.
I noted that the duckbill, that the change in that sort of centered around when the chuck flub impact was in Mexico. And so while you were talking, I looked on my cell phone on Google to find out about what the angle of that impact was. And now I have lost my note. I think they said it was between 35 and 60 degree impact from the northeast, but I don't know how that would affect something this far away. But it was a pretty big impact. But I just thought it was interesting that that duckbill kind of centered around when that impact was, and was about the time that that sort of reversed course. I just, thought that was interesting. I was noting the dates on there and thinking, well, that's funny. Why would that be such an extreme change? Yeah, like that. Why would there be such an extreme change at that one point? What happened in that point in history that would have caused such a distinct reversal?
Well, I guess what I would say is that point changes aerially. So the rollback starts at different times depending where you are. And
Right.
The rollback appeared to start earlier on the north than in the south from everything I've seen.
Yeah.
So there isn't one time that we can point to for the rollback.
Oh, I'm sure, but it's just that general area. You just wonder for something to be that big a reversal.
Okay.
In a graph, there have to be either a confluence of different impacts, or a single event. And I just happened to look over there at where it was in history and thought, oh, that was about the same time as when the crater was formed, rather. And then the other thing that I had was, you were mentioning about the blockage at the south end of, I think it was there's a Florescent Lake.
Yes.
And how steep it was in that lake. And
Yes.
And maybe you said it and I didn't hear it. You were talking about how steep the banks are. And I wondered if that was partly because of some faulting that had taken place much earlier, and or both, whatever, and that before the Lahar formed, if there was a very deep river that had run through there. And that was why it was so narrow and deep, was because it had this long-standing river through there that had worn it down. And then once the Lahar formed, it eventually, pretty much forms a dam, and the river is forced to go somewhere else.
Well, a couple things. One, it looks like the early valley was quite gentle. So I had one set of contours based really on what we see at the surface and the surface mapping. And that shows very widely spaced 100-foot contours. Then when you start to look in the subsurface data, the water wells,
right,
you find that there's a very different look to that river valley. And it is a steep, deep canyon.
Yeah.
That would post-date that gentle canyon.
Yeah.
And then yes, you get the Lahar and the lake sediments burying that canyon.
Right.
I'm forgetting where I was going with that. But
you're just saying that to make me feel better, right?
No, anyway, so and that's an example again. Oh, I know what I wanted to say. It's an example again of the development of an antecedent, drainage, cutting down, and how quickly that can happen. The other thing is, oftentimes you'll get volcanics blocking these rivers, like the Grand Canyon, the Cederstrand, and the river doesn't care. It wipes that dam out in a nanosecond. And I suspect that The reason it didn't happen in this case is because of the uplift. The uplift is, keeping that river from wanting to go down its old valley because it's getting its whole drainage reversed out.
Yeah. Well, it's going to it's going to escape, keep building up until it finds a shorter route down.
Yeah.
Yeah.
I think I think that's the piracy. So that's my point would be that it's because it got taken out from behind.
Yeah. Yeah.
Well, Bob, I
Thank you.
You're going to teach me more about piracy. I just have had a hard time visualizing it and knowing, what's working its way headward to pirate this thing.
Well, I think that's that you asked what the future is. I think the future is people looking at drainage evolution from the standpoint of what are the operative things that can actually make a drainage change. And I think that there will be headward erosion coming up from I'm trying to get Woodland Park. Something's going to come up to grab the water.
Yeah.
And I think that's what we need to think about: water flowing downhill through time. And
I think there's a whole other level of investigation, like you're talking about. This is work that Vince Matthews and Matt Morgan have done, and this is for the Rampart Range, just looking at details of the topography and the lineaments, and the rivers are still, like the South Platte, current day looks like it's controlled by some kind of a lineament. So,
hey Ned,
yeah,
I was just looking on a geologic map to try to see if I could find an answer to your question on the South Platte.
okay.
And I just happened to notice that the senior author on the map is Chester A. Ruhlman, and I wonder if Cal could maybe comment on that.
Well, he had to leave.
No, actually, I was able to pop back in, but I'm sitting in the car and now I'm zooming on my telephone.
All right, Cal, what's the answer?
Well, okay, so with the Pleistocene episode that Ned and I have discussed, and Bob as well, and we're really looking at 200 to 350 meters of topographic development in, say, the past million years, just to be flexible with when these big ice ages started. But we've been able to demonstrate from the Black Canyon down the Rio Grande, and now we're starting to pull things together to show on the South Platte that the incision between North and South Table Mountains and canyons that are generally less than 300 meters in depth can easily be carved in 500,000 years. And again, as Bob has said, it's piracy, or it's some upstream process that is redirecting that water. And in the Pleistocene, it would be high elevation, gentle topography that is deeply incised. And that's what we see throughout the parks and so forth throughout Colorado. And many of those have what were previously interpreted as tertiary Oligocene to Miocene gravels up there, have relationships that could easily be glacial in origin, as long as you've got abundant elevation above it. You can generate ice and outwash that can drape across. So it's on lap. So in many of these places where the Rocky Mountain surface goes above 8,500 to 9,000 feet, you've also got 13,000 foot peaks above it that were covered by large ice sheets and big glaciers before the ice was actually captured into these drainages and producing big moraines like Turquoise Lake and Twin Lakes. And all of that stuff is apparently 250,000 years and younger, that's all nested down in the valleys. So what happened with incising the parks that sit up above it 1,000 feet? And really, I think what I'm attempting to do is to back out 200 to 300 meters of probable Pleistocene incision and see where we are there. And in a lot of cases, we're right at Ned's Rocky Mountain surface, and you've just had upslope onlap by glacial action. If that made sense at all.
Okay. Well, Bob,
So it's upslope onlap from ice carapaces that have generated these glacial deposits that are much different in character than the younger, if you will, Pinedale and Bull Lake, or let's say the last 200,000 years of fervent glacial activity. Before you had deep canyon incision, you still had ice forming, and you didn't have the topography to generate dirty glaciers, and the glaciers weren't nested down into canyons. You had very subtle topography that ice was developing from 14,000 feet down to, and Atwood and Mather would say 7,500 feet in some places elevation, just due to the gentle slope and the absence of any profound topography that would have buttressed or redirected the ice.
okay. Yeah, I mean, Cal, that's why I say I grab points that are possibly as young as Pliocene, or maybe even oldest Pleistocene. I'm happy including points in my map that are pretty much indicating what the topography looked like pre-glaciation. So
Yeah.
I'll take the oldest Pleistocene deposits and include them in my map. I won't go any younger than that. But
Right. And then everything from that is all just incision of that surface.
right.
So it's really not development of that surface, but just incision of the surface, 200 to 300 meters. And that seems to be pretty evident around the southern Rocky Mountains, even in the Wind Rivers.
Well, the other thing I'd point out to the group is if you just look at something like the Castle Rock drainage system, I mean, that's a major river system that's flowing southeast. And what's it doing now? All the streams are flowing north. I mean, it's been a wholesale reversal and inversion of those streams. And what's doing it? Structure is doing it. It isn't really a process of stream capture. There's nobody captured the Castle Rock conglomerate and caused it to go from southeast draining to north draining. The structure caused it to do that. So I'm happy to look at stream capture, but I think there's a much bigger force going on here, and that's these domes that are, hundreds of miles across. They're truly first order processes going on.
Sure. And I'm with you on that. I'm just looking at the youngest incision interval where you can even look at most of your profiles where you've smoothed over the deformed Rocky Mountain surface over the domes. And with the modern topography, you can easily pull out 200 to 300 meters of that deep canyon incision. Okay. And it's really just that. It's not development of the Rocky Mountain. It's ultimate abandonment.
Right.
And so I guess one more simplified way of saying it is, when was the Rocky Mountain surface ultimately abandoned? And I would say the early Pleistocene deposits on that surface in some places with abandonment post that, ultimate abandonment.
And I would suspect it depends where you are, whether it's
exactly. Yes, most certainly. But you can see it. You can see it even around Mount Evans and just right up slope from the Denver Basin, where with Mount Evans drainage and the development of the South Platte and Bear Creek. And in that relationship and where glacial deposits sit high in the landscape, and looking at those relationships.
Yeah, and I pulled up Vince's map because I think that, there's just a whole new level, an additional level of detail that goes into this whole story. And I've seen what you've done in a lot of places, Cal, and you're looking at faults on the order of what we're looking at on Vince's map all over the place, and what they've done to impede these gravel deposits and allow them. You're getting at 1 to 2 mile size faults and gravel deposits and accommodation space up in the mountains to break out these different blocks, and that's a level I've not gone to.
Well, Vince can elaborate, but yeah, we've been talking about the neogene tectonism across the Front Range into the west, and Vince has been extremely guiding in his original interpretations in that, and I think that Vince is right on what he's seen, even faults that are on the west side of Mount Evans and come up through South Part, stitching together the Chase Gulch normal faulting and some of that minor extension through there. But it seems like in some places it's dispersed across broad fault zones, with any one given fault having tens to possibly 100 meters of displacement to major, where they consolidate into major fault zones like the Saguache or the Sangre, or, as Glenn Scott originally had interpreted as substantial neogene faulting in the Wet Mountain Valley. And that's one of the things that I've been starting to look at in more detail, is what is going on between the crest of the Wet Mountains and the crest of the Sangre de Cristos, and your Rocky Mountain surface that would drape over that, how you've depressed that basin and captured Oligocene to Miocene volcanics in there, and then potentially even having Yellowstone tephras captured in there and within closed basin sediments, and then all capped by glacial deposits and then incised. So
well,
I think
it's a
we're
beautiful
coming
place to work.
I think it's really fascinating to me, coming from the, what I'm trying to parse out of the landscape is what incision and what topography has been developed in the last 500,000 years, with big glacial intervals and long interglacials, which we didn't have prior to the middle early Pleistocene transition. And so you weren't melting out all the ice. But the one thing that I think that we keep kind of losing track of is that when we go into a glacial episode and we drop the temperature 6 to 8 degrees per se, if you will, that even during the winter time, the little spring by my house, that I have about 15 to 20 meters, depending on where in size, little arroyo back behind my house up at 7,500 feet. And that is solely formed by a spring that comes out of it that freezes over, develops an ice pack in there that almost instantaneously melts out in the summer and causes massive incision up that. And then it's dead. There's no more activity. So it's like, whenever we're at elevation during an ice age, we develop ice and erosional capabilities that is non-existent during interglacials, which is intuitive. But it's kind of finding those relic, where is that ice forming? And it's not glacial, but it's remnant resonant ice that's got to melt out of the landscape, and so it's going to feed the main trunk stream or river that in my case, mine would feed Bear Creek, and it's caused some of the it aids the incision of Bear Creek during the glacial interglacial transition meltout phase. So mine is a much more simplistic backing out what incision we know has occurred and can occur, and it's more localized, and every single example is really a local local site in and of itself, and all aspects have to be considered, like even things like Bergen Peak right up from Evergreen along the parkway there during the ice age. Even Bull Lake and Pinedale, it's generated little tiny ice snowfields that cause erosion and deposition that is gone now, but it explains all the kinds of landforms and striated surfaces, nivation hollows, and all these relic landforms from the ice ages.
Ned,
Yeah.
Hi. I was just thinking, couldn't it be both of these processes working together? I mean, it doesn't seem like there would necessarily be any conflict between piracy and the big structural uplift or doming that you're talking about. The two would be doing working simultaneously.
Yes, I think that's possible. I'll just say that I'm less comfortable figuring out piracy than I am seeing a big structure. That's
Yeah,
it's my own ignorance. So.
Okay, I see. Well, I mean, it's like that would take a lot of, I guess, detailed work to figure out how that happened.
Yeah.
So Ned, it seems like as we've been talking since prior to you presenting this in Phoenix, that it seems like all this supports also, which is good in my mind, that there's neogene tectonism in the Front Range, and that it's very evident, including like north of Woodland Park going up through Manitou Park, up towards Cheeseman and so forth.
Well, Cal, I guess my point is, I think people have said that before, that there's lots of neogene stuff. What I'm trying to emphasize is that it isn't just neogene. Things were happening in the Paleogene. What I kept hearing is Miocene, a pyrogenic uplift. Everything's happened since the Miocene. Everything's younger than 6 million years. And I kept running into stuff that didn't really seem that way. And that's why I went back to the Florescent Valley, because I knew that was one of the major criticisms of the model I was putting forward, or one of the biggest problems with the model I was putting forward is if the lakes are being dammed by the volcanics, the dome could have been much younger than the formation of Florescent Lake.
Ned, I think we're in a transition period of thinking, and you've transformed your thinking from when I first started talking to you. But when I came to Colorado, the dogma that was being taught in every single higher education institution in this state was that all of the tectonic activity was during the Laramide. It was eroded off at the end of the Laramide, and all of the faults have been dead since the Laramide. And that was the dogma. And it really wasn't until Glenn Scott in 1970 put out a little paper talking about, he thought there was some young tectonism, but there has making that shift from realizing what's been going on since the Laramide has been very, very slow in the academic community. I've watched it over the last 5 decades, I guess. And we think of academia as being forward thinking and jumping on a new ideas, and I'm not sure exactly the case. So there's probably, we're still working on that transition to thinking that, yeah, there was laramide, and Bob and I have talked about how high were the laramide mountains, and I'm not sure we still have a handle on that. And until this tremendous tens of thousands of feet of displacement post laramide. I mean, it's a tectonic. People talk about epeirogeny. I looked that up because I wondered why I had a problem with people using epeirogeny to describe the neogene. And I would say that the neogene is, according to the definitions that I found, the neogene is much better described as an orogenic event than an epeirogenic event.
Yeah.
Okay.
It's economic incentive versus good scientific thought that's driven the last 30 years.
Well,
Hey, wait a minute, Cal.
one thing that, there's a coincidence of opportunity because of the increased capacity to measure surface displacement. And to answer Vince's point about, are we in and Ned's point too, is the laramide continuing to today? And is the neogene a time of orogeny instead of epirogeny or stasis? We're actually we'll start to see it. I mean, someone's going to be measuring measurable uplift, and they'll be, we're at that the happy, joyous coincidence of our measuring systems are getting good enough that if there is ongoing tectonism, we will see it. It'll be in radar interferometry or whatever that thing is. I mean, there'll be ways in which someone's going to notice that things are moving if they are moving.
But Bob, we've already shown that. We haven't shown vertical because there's a little more difficulty with that. But the GPS campaigns that have been done by a number of groups all show that this stuff is moving actively today, that the Rio Grande Rift by Leadville is as active as by Albuquerque, which people were trying to say for a long time that it was kind of dead up by Leadville, but it's just as active today. We're measuring it today as what they're measuring today in Albuquerque in the Rio Grande Rift.
Well, I mean, we know it breaks the moraines at Chalk Cliffs. So the rift is active. I get it, but is are your lineaments, for example, in the Rampart range, to take the map that's on the screen right now, it'd be interesting to take that piece of territory and say, is anything wiggling?
Well, that's being done right now. There's a National Earthquake Hazard Reduction Program grant to Jim McAlpin and Matt Morgan to study that exact issue right now. They're in the middle of that grant.
Yeah, good.
In the Rampart range?
On the flank. The Ute Pass Fault, which is the boundary between the Rampart Range and Pikes Peak.
Well,
that fault's been active, since the latter part of the Proterozoic in the ancestral Rockies and the Laramide. Why would it stop?
Well, that's true.
You know what's another interesting point, that even all the way up through the Cordillera and what we're seeing even up in Alaska and up in central Alaska, we're starting to see that tectonism up there, just Ned, that you're saying is Oligocene to the present. That's exactly what they're starting to see, that in the same general vicinity that you've had, it's reorganized itself, whether it's going from purely compressional to transpressional to now transtensional. It's still ongoing tectonism that's really Oligocene through the Miocene into the present. And it's ongoing. The whole Cordilleran is just deforming in a different fashion.
And I think, Ned, Cal and I believe are on the same page with this. If we look at just the Cenozoic, we've got, I mean, it's pretty clear that you were in and continuing in the Laramide, which was one type of orogeny. It was under a lot of confining pressure. It had maybe 12 to 15,000 feet of overburden across the whole state. And so that was occurring at that time. And then we had this period of incredible caldera eruption. And I don't think I would put that in the laramide orogeny. I don't think it belongs in there. It's a totally different type of thing. And I think that then we changed at about 25 million years to this extensional environment. We had basaltic volcanism instead of calc-alkaline volcanism. So I don't think it's very difficult to say we had three discrete periods of activity during the Cenozoic: the laramide, caldera period of volcanic eruption, and the extensional neogene uplift and basaltic volcanism. Why would you? I know you're a lumper, and I know I'm a splitter, but I don't understand why you'd want to take those three really distinctly different. They overlap in time, but why would you want to take the three distinctly different events and lump them together as one?
I would just lump them by saying they're all part of an orogenic cycle that's driven by slab behavior. And
I wouldn't disagree with slab behavior.
Yeah.
Read Matthews 1978.
No, and I know you don't disagree, Vince. I'm just saying there are phases of this slab behavior that set up, distinctly different styles of tektonism, of structuring.
I agree completely.
But they're not just out there floating around completely independent. They're part of differences in what that slab is doing through time, right?
Absolutely.
Yeah, I see what you're saying. Yeah.
And it's not just time, it's through space. I mean, you can be thrusting, down in Colorado while you're extending up in northern Montana. I mean,
one spot that
that's
Carl
what ties
Kellogg,
it all together, I think. Yeah.
Carl Kellogg and I went out to Winnegar Ridge and Iron Mountain at the early winter, late fall, November, this last November, got out there before the snow and had a couple other folks with us, Dan Moose and Meredith Reheis, and the Winnegar Ridge gravel up there that Carl has looked at for a long time, right next to his vacation home, and he was always under the impression that it's an Oligocene or Miocene, just like the Central City gravel. And now it was my first, just not when I came into the area and started working, I hadn't necessarily been steeped in the background, the precedent and background perspectives that Vince was mentioning a minute ago. And so to me, my first impression was this was tilled, just very much like the Central City gravel. And then, so Carl is now on that board. And then now what we're seeing is those faults that come through Iron Mountain that are west dipping appear to be antithetic to some east dipping structure that runs along the east side of the divide, right at the base of the slope. And it forms a graben that Nederland is sitting in. And it appears like those gravels, however old they are, have displacement across them. This would be a great field trip, accessible to many people. And but we're starting to see, if those gravels are middle Pleistocene, glacial and glaciofluvial deposits, then you've got 10 to 20 meters of offset on, let's say, a 500,000-year-old deposit. And that gives us about 1/10 of a millimeter per year of displacement, long-term tektonism. And that's exactly what all the geodetics are showing, that we're moving at 1/10 to 3/10 of a millimeter per year. And that the regional neotectonic framework of the region would say that faults generally, major faults, are moving on that order of magnitude, which is rift equivalent.
Okay. All right.
but that's
Well-
another discussion.
No. Well, it's 3:12. Are we, this has been a nice discussion. Anybody else want to chime in before we sign off?
We gotta get Beth to sign up that field trip that Cal was talking about.
Yeah, that would be very easy to do, and we could actually start it at Carl's cabin up there, right on the Magnolia Drive or up there. It's easily accessible, and it's just a gentleman and ladies and gentlemen stroll across the meadow and up onto the gravel, and then you can walk along it out towards the Iron Mountain and see where it's overlies bedrock, and then lo and behold, there's a mine there that's in shattered, sheared, and fractured rock that's been hydrothermally altered, and that fault's probably had, as Ned's indicating, a long history of movement, but it's slow rates. So, a tenth of a millimeter to even less than that, generating earthquakes on the scale of every 100,000 years to create displacement along it.
Well, make it so.
Yeah, that would be something we could do this spring sometime soon.
Cal, for CSS, we're putting together a field trip to White Rocks and to Marshall Mesa. Just since you're the field trip coordinator, you might want to know that.
That sounds great.
Okay, that's probably going to be early fall, late summer, early fall.
When you've got something planned, just let me know, and then we can. Yeah.
So
hopefully it sounds like it wouldn't be that difficult logistically.
No, it's for the Boulder Weld fault system up there. So
that sounds great.
Yeah.
Ned or Bob, maybe this isn't the time for it, but at some point I'd like to hear more about your 9 days from Uray over to Lake City. Any advice or logistics or anything that you learned that maybe you could pass along? It sounds like a great hike.
Yeah. If you would email me, do you have my email?
I think I do. I'm pretty sure. Yeah, you're on the FSS list, right?
Yeah.
So I've got it there if nowhere else. Yeah.
Just drop me an email. It was a glorious trip. We had a great time.
Oh my goodness.
And I'll just say for me, it's so instructive just to be out there looking at the landforms. I mean, we walked into the Needles Mountains and it was like, oh my God, we're in the middle of a Neogene uplift. And we were. I mean, you just don't get that kind of extreme topographic relief in something that's old. So.
Ned, I have one more question. With the Ute Pass fault, and probably Bob and Vince can contribute to it too, but isn't that the location where you've got divide gravel on either side of it? Yeah.
So if you go,
that's one of the locations where in the footwall of the fault, you've probably got right now in my thinking, you've got an older gravel perched up there with a younger inset, and due to reworking of these old well-seated paleofluves that were broader and lazier, if you will, that you've got the younger, the deposit on the hanging wall it would be that onlap of Pleistocene deposits that's well below the Miocene or Oligocene gravels that are up in the footwall of the fault. And I don't know, you've just told me about it.
Well, I'll give you this, that this is Rampart Range Reservoir. So, you know, there's Pikes Peak and you're up on top of the Rampart Range. Mm-hmm. And these are mapped as divide gravels. They look a hell of a lot different from, the stuff up by divide.
Mm-hmm. The divide gravels are
I'm puzzled
here's the stuff west of Divide.
Yeah.
Anyway, so I think, I would suggest that the whole system needs a lot more study.
Well, and I think that you've really emphasized something right there, Ned, and that is that a lot of people think that Colorado's all mapped and there's nothing left to discover. And there is a tremendous amount of field work that still needs to be done that we're in such an elemental stage in the mapping in the state of Colorado that it's almost frightening. And virtually every quadrangle that the Colorado Geological Survey maps, they come up with unknown, brand new, exciting stuff.
Yeah.
And yet you got the academic institutions saying, mapping's past tense. We're not interested. We don't want our students to learn mapping. We want everything done on a computer. And of course, it doesn't change on a computer. The old adage from the first time computers came out of garbage in, garbage out. If you don't have the real what's on the ground that you're putting into your computer, you can forget about it. It'd probably be better not to do it.
Oh, it looks pretty.
Oh yeah, it looks pretty.
Yeah.
And it leads to all kinds of wonderful conclusions. I'm thinking about students who have never done any field work. And the schools who are doing away with field camps and all of that sort of thing.
Really? Wow.
And Ned, we've been talking for since Phoenix about getting out in the field and you showing me these.
No.
We need to do that.
You've been talking about getting out of the field. I've been in the field, Cal. Where are you? Come on, baby.
Did you see the picture of the 9-day trip?
Yeah, this is Bob. Let me find it. Wherever it is. It's going to be 15.
Somebody that ran across you guys on that trip but said, gee, that old man with Ned was doing a pretty good job. He was keeping up pretty well.
Who's this?
Might start with a C.
Yeah, no, Ned would indicate with some kind of a stick where I was supposed to get off the trail. He'd be sitting there having dinner and I'd show up.
Well, the fact is, Vince, that Bob kept going. I was about to drop in my tracks. Unfortunately, the snow came in. So anyway, I will say that hike between Ouray and Lake City is absolutely glorious. You get up into this high country and there's nothing better. It's just nothing better. It's beautiful. All right. Well, why don't we sign off? This has been a pleasure and thank you all for listening. So
thanks, Ned.
Yeah, my pleasure. And I hope to see everybody soon in person.
Yes.
In person.
Thank you, Ned.
All right. I'm going to sign off.